Hi, so I'm presenting a paper on the B matching problem. It's a classic problem, but we are studying it from an online perspective. And this is motivated by applications in reconfigurable data center networks. So this is joint work with Marcin Bienkowski, David Fuchssteiner, Jacek Marcinkowski, and myself. So many of you, even today, have probably used data-centric applications many times. So these applications are related to science, entertainment, social networking, gaming, and all of these applications are running in data centers. And the traffic for these distributed applications is rising quickly in data centers. So the interconnecting networks in data centers have become a critical infrastructure of our digital society. And the problem is that the network equipment is approaching capacity limits. So transistor density rates are stalling, power density rates are stalling. And this has also been referred to as the end of Moore's law in networking. And this means that we need more and more equipment and larger networks, and this is resource intensive and inefficient. One cause of this inefficiency is related to the way we interconnect racks today in the data center. So of course there are many different flavors how this is done today, but all of these data centers today have in common that they are fixed and oblivious to the actual traffic demand that they serve. And this, you can think of it like building a highway that in a way that is unaware of the actual demand. So as you see in this example, there may be a lot of traffic jam on one side, and it would be actually much better if you could also use some additional lanes on the other side. There is a lot of free capacity if you would design the highway in a demand-aware manner. So it can be quite frustrating to have these resources not used efficiently, and our vision is that we want to change this and make the data center demand-aware. So we call this vision self-adjusting networks. So the interconnect between the racks should become flexible. And for example, if the demand matrix is like this, then the racks should be interconnected as follows. Maybe later the demand matrix, so in this way it would match the demand. If later the demand matrix changes to a pattern like that, for example, then again we can change the interconnect accordingly. So we could interconnect it like this. So again, it would match the demand. And we refer to this vision as self-adjusting networks because they adjust themselves towards the demand. The interconnect depends on the demand. In reality, the architectures that we have today are or proposed in the literature, they are mainly hybrid architecture. So it means they combine a static network and dynamic network. And the static network is used for small flows, typically for mice flows that are latency critical. And the optimized network is there for the big flows that are also called elephant flows. And in combination, these architectures can kind of provide the best of both worlds, like good flow completion time, both for large flows and also for small flows. The technology that enables this vision is based on emerging optical devices. That one of them is shown here, the optical circuit switch, which allows to change the matching between inputs and outputs by allowing to rotate the mirror. Here there are some mirrors at the bottom, and they allow to change the interconnect of the switch. And each OCS or each optical circuit switch provides such a matching. And if we take multiple of those OCS switches, let's say we take P of them, we get a model where we can add to the topology a B matching on top. So the optical switches can add a B matching to the topology. There are many different prototypes of this technology related to or using silicon photonics, NEMS, rotating disk, etc. But for now, in this paper, we mainly want to focus on the algorithmic aspect of this technology. Good, so I'll first present the model, and then give you an overview of the algorithm and the lower bound. So we present the optimal, asymptotically optimal algorithm that is B competitive, and finally we conclude with some simulation results. So we are given as an input to our problem a hybrid network that is, on the one hand, the fixed network is there, that is fixed, that is static, so it's an arbitrary graph. And on top of it, we have B OCS switches that can provide a B matching. The demand or communication demand comes in requests over time. So we have pairs of ST, source destination pairs that arrive over time and have a certain demand. And the output of the algorithm should be a B matching over time. So we have a sequence of B matching, so how we adapt the flexible interconnect. And since changing an optical link takes a certain amount of time, we model this with additional cost, that is cost alpha. So each time we add and remove a link from the B matching, we pay alpha, and the other cost that we have is a routing cost. So if you have to route a request along the fixed network, it costs the distance in that network. And if you can use the direct optical link, it costs 0. So here, if you would establish a direct connection here, then this would cost 0. Otherwise, we have to go along the topology. Our objective is to come up with an online algorithm that optimizes the competitive ratio, so that minimizes the cost the online algorithm has compared to the cost of an optimal offline algorithm that knows the entire sequence ahead of time. So let's get into the technical results. Important observation, or intriguing observation actually in this context, is that the problem of online B matching is related to a classic optimization problem or classic online problem, namely paging or online caching. And you can think of it like this way, that if a node has B possible optical links, you can see these B possible links as a cache, and it contains at most B items. So if a request is in the cache, we can serve the request at cost 0. Otherwise, we have to pay distance D in the network, and fetching an item into the cache or establishing a link costs alpha. And this is known as online paging with bypassing, because I can also serve a request without it being in the cache. But there is still a difference between the two models. You cannot just simply apply online paging independently at each node, because there is a coherence issue, because the two nodes need to agree. So the laser and the receiver, they need to agree that they establish this link. So these decisions may conflict. So that's one of the challenges in this model. And nevertheless, to derive a lower bound, we can actually make a reduction to online caching. So to see why any deterministic online algorithm has a competitive ratio of at least B, we can assume a star graph, which has B plus 2 nodes. And edge lengths in this graph are 1. And initially, the matching is as such that we just connect the center to the B leaves. And now what the adversary can do, it can always request the missing node that is not in the matching, alpha times. And we call this alpha times requesting this node a chunk. And it's easy to see that any deterministic online algorithm has to pay at least alpha per chunk. The offline algorithm, the optimal offline algorithm, instead, it can just choose a different matching and will pay alpha times k divided by b for k chunks. So this is the lower bound, but we also present in the paper an upper bound, online algorithm, deterministic one that is matching this lower bound, that is B competitive. So the idea of this algorithm is to have a counter for each edge. And usually this counter denotes the number of times E was requested since the last eviction. And if this counter reaches alpha, then the edge becomes saturated. And if the edge is saturated, it is in the matching. That's actually a little bit simplification, because it turns out it's more complicated to get this competitive ratio, because when the counter of an edge is equal to alpha, you and we still need to run an agreement scheme. Okay, so this agreement scheme here, we give an example for b equals 3. So there are two cases. The easy case is if after marking u and v saturated, then the number of saturated edges at most b. So in this case, there is no problem. But in the other case, if u and v cannot become saturated, as u would already have too many incident saturated edges, we need to do something about it. And in our algorithm, to make the agreement, we reset all the counters for the edges incident to u to 0. So now in this case, we have to reset the counters, and that's also one of the challenges we face then in the analysis. So the approach that we follow is a lazy one. So we have a lazy saturation scheme. So then if the edge is saturated, then we have it in the matching. And when the edge stops being saturated, so it is reset to 0. It is not removed from the matching, but it's just considered as a candidate for future removal. Okay, so and then for the analysis, we can proceed as follows. We say that when the b plus 1th edge incident to a node w becomes saturated, this can be seen as a witness that opt has to pay at least alpha for the requests that correspond to the saturated edges. And the hard part of the proof here is that we cannot simply make this argument for a single node w, as its incident edges may be reset multiple times, and hence the online algorithm's cost with w may in principle be much larger than b plus 1 times alpha. Good, so just to conclude with some simulation results, we are using different traces. We also made them available on a website that are coming from Microsoft Datacenter, Facebook Datacenter, but also synthetic traces from pFabric. And a micro benchmark we consider here in the paper to evaluate our algorithm is the cache hit ratio. So we see that especially for pFabric and Microsoft workloads, there is quite a good probability that a link is an optical link is already in the cache. And this is actually as expected, because the empirical studies on these traces also show they have quite a strong locality or temporal locality. Regarding routing costs, so here I just show the Facebook data set. We see that our algorithms always perform better than the oblivious approach baseline. And actually, the online BMA algorithm that we presented performs quite close to the static algorithm, although the static algorithm knows ahead of time the distribution of the requests. And actually, we believe that if we had longer request sequences, we could also see that the online BMA algorithm significantly outperforms the static algorithm. Good, so we present asymptotic optimal online B-matching algorithm, which we believe is quite intriguing perspective, because the algorithm is also kind of naturally decentralized, and having distributed control planes for these reconfigurable networks is something that seems very appealing. And we also believe that the online B-matching problem is, of course, of interest beyond the application domain we have considered here. So we believe this this algorithm may be relevant elsewhere. And as a future research direction, we would like to suggest considering randomized algorithms that turn out to be harder to devise than one would think. So this reduction to caching that we exploited in this paper seems not so easy to extend to the randomized setting. Thank you.